off.
The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. This is Jennifer Beliveau, Director of Sales from Applied Math Modeling, and today's moderator. Thanks for joining us today for improving the efficiency of data centers. With me on the line is Paul Venus, Applied Math Modeling's President and CEO, and Matthew Allen of Facility Support Services. Before we get started, we just want to inform you, as always, we have a question and answer session at the end of today's presentation. You can enter your questions in the question panel that's located on the right-hand side of your screen. If you do have any technical difficulties during the presentation, just click on the raised hand icon and we'll respond to you through the chat window. So if you look through the chat window, that's how we'll be keeping track of you. So without further delay, let's get started. Paul?
Hi, Jennifer. Hello, Matt. Hello, and welcome to our show.
Hello.
I want to thank you for coming, and I'm going to do a couple of slides here first introducing us, all of us. I know that many of you do know us at Applied Math Modeling, CoolSim and all, and so I don't want to dwell too much on it, but we are a spin-out of the Ansys Corporation. We're actually a partner of them. We do add to their base technology with CoolSim, of course, for data centers. And we are responsible for all the sales and development and support for the CoolSim data center modeling application. It is a little bit different in how it's delivered. It's delivered as a SaaS-based implementation, software as a service. If you're not familiar with that, it means that we do the heavy computation on a cloud-based infrastructure, remote infrastructure. That gives you better cost effectivity because you don't have to buy that infrastructure. You just use it or pay for it when you use it. And furthermore, the price of the solution can scale with use so that if you don't use it a lot, it doesn't cost a lot. So we're trying to deliver cost-effective engineering simulation tools using that method, and that's a unique differentiator for us. We are experts in the field of CFD, not necessarily data center design, and that's why we have Matthew with us today. He's a design expert. And but we are getting a lot better at it over the years and pretty good at modeling data centers and data structures, and can help you with most anything you're going to run into. Now, let me just introduce Matt and let him talk about facility support services. Matt?
Thanks, Paul. My name is Matthew Allen. I work for Facility Support Services. We're located in Beltsville, Maryland. I have approximately 10 years in the data center industry as operations. Facility Support Services, we're a team of professionals. We do 24/7 coverage. We do design, build, QA, QC services. We have an in-house mechanical sister company, and we try to strive to do above and beyond what certain facility management companies can't do. We do integrated facility management. We teamed up with Applied Math Modeling and purchased a CFD modeling, and the way we use it is in a little different aspect to where we use it from an operational approach rather than an engineering approach. So when we go through these slides, we'll explain in detail some of that. But as far as facility support, we're a one-stop shop, basically.
Mm-hmm. So you do it all, Matt, right?
Yes, sir.
Okay, and you're located in the D.C. area, as I understand it, Maryland, right?
The D.C. metro area, correct.
That's right. All right, now I'm going to do a couple of slides here for the audience just to review terminology. I always feel compelled to define my TLAs before I use them, so I'm going to use a couple here in the discussion of these data center variations that we're going to do, and I want to just define them. Most of you know these, so I won't dwell on it too hard. If any of you have questions, get in touch with me after, and I'll explain to you or go through it with you. PUE's the first one. It stands for Power Utilization Effectiveness. It's simply a ratio of the total facility energy divided by the IT energy. There are different levels of PUE. People talk about it in terms of level 1, 2, 3. It has to do with the power coming into the data center and how it's measured. But for purposes of discussion today, what we're doing here is talking about the power going to the IT equipment itself, plus the rest of the energy over here on the left required to drive that data center. And this includes all the cooling power, including the fans to drive the cooling systems, the humidifiers, the in-row coolers, whatever, It also includes the power going to batteries and transfer switches and the inefficiencies of these things. So not only do you have the IT equipment that's consuming power, but oftentimes you will get 10–15% over here in just leakage inefficiencies of that. And it's the sum of those two items compared to the IT energy that characterizes your PUE. So a very high PUE means that, very low PUE is good, and what that means is that this portion of it over here is small compared to the IT equipment. Now, what a lot of people don't understand is that the chiller and cooling system itself are the dominant characteristics of the non-IT load. They are the sort of the tall poles in the tent, to use a metaphor. They're the ones consuming most of the energy. And what we find a lot is that the energy consumed by the cooling system is often nearly equal to what's being consumed by the IT system. And that's a lot of what we're going to be talking about here today is how do you reduce that? How do you get that back down so that your cooling system does not become a dominant characteristic in terms of your power consumption? These things can consume a lot of power. You have to remember that in some cases you're talking about megawatts of data, and the consumption of electricity in a large data center can be in the range of $500,000 a month. So this is a lot of money that we're talking about here, and the opportunity to reduce it by 25–30% is quite good. Now, you want to have a low PUE, of course, because we're measuring the ratio in the numerator of total facility power compared to IT power. So you'd like to drive that thing to 1. If you could drive it to 1, it means that you're only powering the IT equipment alone, and you don't have to pay for anything else. Not really reasonable unless you're doing completely free cooling, and even then there's fans. So getting down to about 1.2 is very good. Or excellent. Good is typically 1.4, but you often see them around 1.8, or we see them a lot at 2.0. We really see them at very high, which means you're paying a kilowatt for every kilowatt you're using to power your IT equipment. You're using another kilowatt to get the heat back out of the room. DCIE is another acronym or another term used. It's the inverse of PUE. It's not used as much anymore as PUE. Here you'd like to see it up around 85%, and typical is around 55%. Now, another one that we often talk about and we'll be using here today is called the RTI. The RTI is really just a ratio of the air required by the IT equipment compared to the air being delivered into the room. You'd like this, again, to be a 1-to-1 ratio. You should not have to pump more air into the room than the servers need. And the servers need air dictated by their thermal load. The ratio is roughly about 156 CFM per kW if you're assuming a 20-degree delta across the servers. It's about 100 CFM if you're assuming a 30-degree delta. So you can literally sum up the IT load in your room, multiply it times one of those numbers, 100 or 156, and know what your cooling system should be delivering for air. Now, it doesn't mean that that air all gets to the right place, and that's a lot of what we'll be talking about today. But at least knowing what this ratio is very important for you because it gives you a feel for understanding how much cooling you have, if you have too much cooling, etc. The other metric we'll be using today is called RCI. This is another metric that looks at conformance of the ASHRAE specification for rack inlet temperature. How well are the racks in your particular data center conforming to this standard? And here we're looking at a Class I standard here of 64 to 80 Fahrenheit, or 59 to roughly 90 of, well, that's allowable, but 64 to 80 unrecommended. We generally look at the recommended side of it. That's what people are most comfortable with. You can drive them up a little higher, and with new ASHRAE specifications, these are going even higher. But, Matt, I think you'll agree it's a challenge to get people to even think about rack inlets at 80 degrees, much less 90 degrees, right?
That's correct.
Generally, what we find in the data center is it's too cold. People are running them too cold, and they're blowing too much air. That's often what we find. So trying to drive up supply air temperature can save an awful lot of money. Open the window of the economizer if you have one. and trying to increase overall temperature in the room is generally a good thing. So RCI is a measure of that. RCI high looks at how many of the racks are too hot. Are they out of conformance with the high end of the spec? And low is how many are out of spec with the low end of the specification. So you'd like them to be 100%. 100% is great. You get them towards, that end is really what you want to do. Less than 90, not so good. So in today's data center, this is one of Matt's. It's not my data center. It's one he worked on. I'll let you take us through it a little bit here and describe this, Matt. You want to just describe what we're going to see?
Sure. So this is a client of ours, and this particular data center it sits on an 11-inch raised floor, and it shares a underfloor plenum with a network operations center that does not consume any airflow. The total space is approximately 3,600 square feet. They had about 73 racks, and the PDUs are set up for an N+1 configuration. They have 5 water-cooled DX crack units, and they have approximately 2-foot extensions on the returns, and pretty much it's just a simple room. It's split down the center with the ramp, and we'll get into that. But that's pretty much the gist layout of this space.
Now, we don't know exactly who this is. They were not sensitive, not comfortable with that, but you're in the Maryland area. You do see an awful lot of government installations, and I guess it's fair to say they're not all pretty, right?
That'd be correct.
So here's, I showed this is from CoolSim 4, but I brought the model into CoolSim 4 to show it as a 3D shot. This is just a shot from the GUI. But let me just take the users through what we're seeing here. The arrows on the top of these racks represent airflow direction. So you see here, these racks are going front to back. The red is cable cutout on the back side. And the first thing I notice here, this one, Matt, is got racks pointing all over the place. So it's kind of mixed up, right?
Yeah, that's correct. There's not a lot of rack architecture layout that was taken into consideration with this design.
And in some cases, I noticed right over here, we've got one pointing in one direction, one pointing in the other, and so we're going to have air going right around in a circle there.
Yep.
And you've also got a couple cases where you're blowing air from front to back into a area where there's perforated tiles in the floor. So, yeah. So we've got some classroom style configurations, which I've run into a couple of different times. That's an older configuration, and you see it over here on the right. Now this is the shared plenum area. This is a knock area over here on the left. Is that correct?
That's correct.
And then underneath you've got a shared plenum. So you used a baffle, but it's open to the underfloor, right?
Yeah. Out of that 3,600 square foot, that knock is approximately 800 to 900 square feet of that.
And you've only got an 11-inch floor. Another thing that I see in old data centers, the floors aren't very deep. And looks like you've put some obstruction under there. You had some obstruction under this floor?
Yeah, as you can see, there is a cable tray, perforated cable tray, and then the smaller lines on the base model here are an actual 6x6 raceway, electrical raceway. Yep. And they had that running right in between the discharge of each crack unit.
Okay, and here's your ramp in the center and so forth. Yep, okay. Yep. So let's take a look at and see what we've got. Now, one of the nice things about CoolSim is you can export all of the results into an HTML doc, and that's what we've done here. So what we're going to show you today is some output. This is all coming out of the new version 4. And the nice thing is that within PowerPoint here, using GoToMeeting, I can sort of manipulate this model around and look at different aspects of it. So here we see underneath the obstruction on the cable trays and the floor tiles and the blockages underneath the floor. So let's first of all take a look at the summary report and see what we've got. So this is a summary of what's going on in the room, and you see we're delivering 51,000. Now this is an N+1 design, so that's going to be a little high anyway, right? Because we've got about 10,000 extra CFM that are coming through there from that +1 crack, right?
Correct.
The flow through the racks is only 30,000, so we really only need 30,000 CFM. And again, this is 196 times 156 gives us this ratio right here, roughly. Total PDU heat load about 4.5 kW. We've got about 40,000 coming through the racks. That's got about 196 kW of total load in the rack itself. Let's go down and take a look at our energy report. Now, this number 1.8 is coefficient of performance. It's another three-letter acronym I did not define. Let me spend just a second on that. Coefficient of performance is simply a ratio of how much energy is required to get the heat out of the room compared to how much energy is going into the room. It's a heat pump kind of idea. It comes from refrigeration. And a good COP for a chilled water system is 4. That means for every 4 kilowatts of load, of IT load, it's only using one mechanical shaft kilowatt of energy to get that heat out of the room. So this number here, your COP, should be up around 3, and it's not. Now these are measurements actually that you made. They're spot measurements. It's not an average, of course, Matt, but it is a spot measurement you made of current at the site, making current measurements off the cooling units, correct?
Correct.
So all we did there is we just did a quick power calculation. It is instantaneous. It's not an average, and these things do vary over time. But nonetheless, what we find is that it's important to get some kind of measurement so that you know where you are in what ballpark you're in, you know, where you are in general with respect to energy efficiency. So if we assume a COP of 1.8, which, by the way, is not unusual, I have seen them as low as 1. Remember that 1 would mean that for every kilowatt of power going to the IT equipment, it's taking me another kilowatt to get that out of the room, to pump it out of the room. Very poor, but not unusual. That would drive the PUE to be 1.6, or the DCIE to be 63%. RTI here is 59, almost 60%. Again, we've got too much airflow in the room. We saw that up above, and you can see it right here in this RTI number. Yet, despite the fact that we've got an RTI number that's really too low, which means there's way too much air being supplied into the room, we have an RCI that's below 100%. This means I've got some hot spots. So I'm not at 100%. I've got hot spots in the room, and I'm too cold. This should be 100% too. So by looking at just this set of numbers right here, you can get a lot of information about what's going on in your data center. By looking at this, I can see that our PUE is awful. Our energy contribution here, our ratio, is awful. Now, RTI is well below where it should be by 40 points. I've got hot spots in the room, and I've got a lot of cold spots in the room. So the cost to run it, assuming in this case 10 cents is what we had in the calculation per kilowatt hour, would be $275,000 a year. And if we take a look at the cracks, you see they're set pretty cold. They're down at 56 degrees, 58. These are measurements that Matt made. The way to do this most effectively for those who are trying to build models is, if it's an existing data center, go into your data center and take a probe and measure the supply temp coming out of the crack, and then use that as a boundary condition in the model. Once you set these, you can then run the model and look at these, see what the model predicts on output, and if they match within 10%, then you're home free. You've at least captured the physics in the room. It's a very quick way to validate your model. And if we go down and now look at our racks, you see here that we're failing. We're failing the recommended standard for a Class I server on the cold side, and that's in blue. But if we scroll down and we go a little further, we're going to see some popping up down here that are in red, because this means it's too hot. Now, data is hard to look at. It's a bunch of data. Of course, it's better to look at it in 3D color. So this is a color representation here. We just added this in our new version 4 of the software. This is a conformance plot, and here we're looking at the conformance of these rack inlets to the ASHRAE specification highlighted here in green. So what I've done on this one is, this is the Class I recommended spec, 64 to 80, and we're looking at rack inlets. How are they doing with respect to conforming to that standard? And you can see when these should be all green in a good case, but I've got problems. I've got them being both too hot and too cold. Now, too cold is a problem because it takes more mechanical shaft power to produce cold. The lower you go in temperature, the more energy you consume. But furthermore, I've got hot spots, so it's fundamentally an issue. And this is the initial state. This is what we call the base case. Now, what I thought I'd do here is show a couple of the pathline plots. This one, Matt, is the air coming out of the tiles. And we've got some hot spots up here, and you can see that our air is not getting up to the top of these racks very well. It looks like you're dissipating pressure before it gets there, so we're not getting good pass through there. And if we look at the hot side, well, first let me show you a couple other things here I noticed, Matt, in this one. I'm sure you've noticed too. This is bypass air. Look at this. This is coming right out of the cooling tiles and back into the crack units themselves.
Yep.
Yeah. So this is bypass airflow, and here we're doing no good at all. It's just going around in a circle, and that's one of the major contributors to energy loss in a data center is what we call bypass short-circuiting is sometimes what it's referred to. So normally this model should show there should be none of these path lines that you can see except for the ones going up into the racks, and then they should stop. But you see we've got a lot of leakage. I mean, look what's going on over here. Very cold, short-circuiting back. But also if we take a look at the hot side, I'm showing you just cold right now. If we take a look at the hot, the air coming from the racks, very hot down in this region, and I think we're going to see it recirculating right back over the top. Yeah, see, it's coming over the top and being sucked into its own intake. And again, that's because the racks are poorly configured. So there we have a very hot situation occurring in this end of the room. So kind of a mess from an air management point of view. All right. So what were you thinking? Take us through your thought process here with respect to improvement.
Well, what we did when we went in and we took a baseline of what the crack operation was. We took supply and return temperatures. We took amp readings. We took static pressure readings. And we took all CFM readings. And then we compare that to what the CFD shows us. And the immediate result was trying to block off that underfloor plenum from the NOC to the data center. So we would like to optimize their existing conditions for the most cost savings, and they really need to define improvements, and they will see widespread change. We recommended hot and cold aisle arrangements, a rack lineup program, a floor tile lineup program. It just was poorly managed.
Yeah. Now, it's hard to go in and tell someone their children are ugly. You have to be diplomatic about this, I guess, right?
That is correct. So we take all the before data that we can capture and use that as an operation, because the crack units have set points that they're supposed to operate to, and all these data points tell you how the operation is going and how the room is going.
Yeah.
And then we just show the customer the facts.
And what you're trying to do, I think, is get them on a get well plan, I suppose, right?
That's correct.
Yeah. And these are some of the needs that they're expressing?
Yes, they had no N+1. It's designed for an N+1, but due to the airflow loss or the static pressure loss in the floor with the NOC, they are using all their crack units to cool the current KW that they have. So they want increased crack operation efficiency, get back to an N+1 cooling configuration. We want to see reduced underfloor leakage, which is ultimately going to increase static pressure and increase CFM.
Yeah.
And then ultimately that will increase the the white space. to where
Yes.
possibly they could have more customers come in or more racks.
Yes, and more reliability as well, of course, yeah. I think it's, and the N+1 is a bit of a misnomer sometimes. Oftentimes people think they have N+1 because the total capacity of their cracks when summed is greater than what they need for their IT load. But until you run a CFD and determine that, in fact, without any of one of the cracks, any given crack, and by the way, you have to shut them all down one at a time to see if you can, if it works. You never really know that you've got an N+1, do you?
No, you don't. There
So
are a lot of variables.
So here's your approach. Split the subfloor, right? Step one.
Yes.
Yeah.
They didn't have, the second one would be implement the rack lineup program. They had multiple racks that had gaps of over 1 inch. So there's bypass air from the hot aisles being able to bypass back into the cold aisles.
Right.
And then improve the efficiency. They had inconsistent set points on the crack units. These are return control cracks, so that's going to have an effect on compressor operation.
Right.
And then align all the racks in a consistent order, whether they be hot aisle or cold aisle setup.
Right. So before we had shared underfloor, raised floor improperly sealed. They weren't using any seals, right?
That's correct. Some of the newer installs seem to have cold locks installed, but 90% of the racks were just a 100% open area.
And you had windows in there.
Yes, this data center is on the edge of a building. It's not on the interior. And there are windows, and the windows just had regular commercial shades, so there was no tent to block any solar load. So we were taking that in consideration because that does add to the, the performance.
Yeah. Okay. So where did you go? Separate the knock, put the cold locks in place, put UV tinting, I guess pretty self-explanatory, right?
Yeah, pretty much. I mean, we wanted to show, I mean, right off the bat, the first thing is to get the airflow back in the floor and not have it leak. So we start off with the knock. We determined the knock didn't need air. So it was served by a building HVAC system. So block off the underfloor plenum, and then obviously the cold locks at each rack location or where any kind of electrical penetrates the data center up the wall or any penetrations through that floor.
Yep. So I took another shot of your first pass here. Want to walk us through this a little bit here? You got cold aisle down the middle, right?
That's correct. So cold aisle down the center of the room. All the racks have been moved in to where there's no spacing between them. All the racks have been turned properly so that their intakes all match and all the exhausts match. And we blocked off the underfloor plenum on this model.
Now, you've got some front to tops here as well, front to rear and front to tops. Older style rack over here as well. Is that an old telco kind of hangover going on there?
It is, and they haven't removed those racks. They're still in use.
Yeah. It's funny how old stuff just kind of lingers. So here we've run this model. Now, this is a cold aisle model, and let's first go to the summary report. There's no containment here. You're still what we call naturally convective on the return. Haven't changed anything here on the flow side or the temperature side. You did move to 60 degrees though on this one. You came up a little bit on temperature, which gave you a little bit better efficiencies. You moved up here to 2.3 on your COP. That's an estimate. You can't always predict these things perfectly, but moving up a little bit is natural because the supply temps came up a little bit. And the RTI is 61%. It's about the same. This was 59 before, so that stayed just about the same. RCI, though, got better. Here before we were in the 90s, but not 100. So that got better. In other words, we're able now to distribute the air more effectively so that there's no hot spots in the room. But it's still very cold. 18.9% means that there's way too much cold air, and there's an opportunity to push that temperature up now a little bit as a result. to improve the overall efficiency of that heat rejection system. So now if we take a look at our rack inlets, again, they're all conforming now. They're too cold. I mean, they're failing on the cold side, which is still not great from an energy point of view, but at least you're not going to have equipment failure in this kind of case. And we see here that right at the tippy top in a couple of places we're starting to get the racks coming into conformance with the specification. However, the only thing you run into when you do cold aisle like this is the room gets kind of warm, and here's a slice at 6 feet of what's going on in that room under these conditions. You got 60-degree air in the center where the cold aisle is, but the rest of the room is 81, 80. Well, it's high 70s up to 80, 82 almost of temperature. So probably lowest cost option from the point of view for them of not putting a ceiling plenum in place or anything, but again, not optimal either, right, Matt?
That's correct. And on this model, everybody can notice we took out all the underfloor obstructions as well.
Yeah. So you've got better air distribution coming out of the floor. If we looked at the crack report, we'd see more even distribution of load on the crack units as well. Let's take a look at the airflow coming from the tiles here and see what we've got for short circuiting. A lot less than we had, so it's much better now. We still have short circuiting going on, bypass, but we're going to have a little because we've got too much air. So that's just going to be the case, but it's certainly not as bad as it was before. And it's not shorting out so badly like it was over in this region. So in general, things are a lot better than they were. Let's see what we've got on the hot side. So if we take a look at the air coming out of the hot side of the racks, this end of the room is the higher density over here, isn't it?
Yes.
Yeah. And we've got some wrapping up around, a little bit sneaking back in, but for the most part, that's not too bad. So that was option number one, design alternative number one. You showed them some others as well. This one's a hot aisle.
Yes. This one here, we wanted to give them the option of a return plenum, which would allow better distribution of the hot air to the cracks, and also from no short cycling.
So what you've done here is right down the center, you've basically changed the racks into the other direction. They're all now cold on the front side, blowing hot to the center. So instead of the center being a cold aisle, the center is a hot aisle here. And you're using a return ceiling plenum. It's probably a drop ceiling in place right there, right?
Correct.
So in terms of expense, this isn't too bad. You do need to extend the cracks up with some sheet metal so they're drawing from that ceiling. You have to make sure that the ceiling's sealed so the perimeter of it isn't going somewhere else. The air is going somewhere else. But putting grills in place, ceiling grills in place, isn't expensive and makes a nice barrier for the hot air to get up. So let's take a look at this one. First of all, let's go back. Well, we'll start at the top. Let's go for the recommended inlet temps here. Now here, because you've done hot, or since you've done hot, we've got even a better situation. I mean, it's still too cold, but the racks themselves are all even. You've got more of an even temperature distribution now than even on the cold. If we take a look at the summary report, and again, everything remains pretty much the same until we get down here. We're still assuming 2.3 for coefficient of performance. The PUE remains the same. But your RTI here, 61, pretty close to where we were before, and that is, again, because we haven't changed the airflow. But the RCI is now 100%, which means you've got no racks in trouble. And the RCI low, still 19, still too cold, but things are improving. It looks to me like the hot aisle configuration is behaving better by a little. If we take a look at the path lines, particularly on the hot side, we'll see that the air is going right up into that ceiling plenum kind of nicely. So there's all our air going right up where it's supposed to be. So that is behaving quite nice. I did notice, however, your front to tops are causing a little bit of trouble right there. And we were looking at this earlier at an eye, and it's because the front to tops aren't getting their air into these grills. It's kind of rolling over the front a little bit. Now, I think the plan you were saying was eventually for them to swap these out. So yes. There's two things they could do here. One is put more ceiling grills in. It doesn't really hurt to have too many unless they get too close to these front ones. But the other thing you could do is you could try putting some curtains in place or something on those, either one. We're not containing here. You haven't contained anything. All you've done is really just line it up and use that return planning.
Correct. Just trying to, for better airflow management.
Yep. Now, the good news about this kind of configuration, again, if we go back to that same plot we were looking at before with respect to temperature, the good news about this is the room's cool. I mean, I prefer hot aisle whenever I can get it, and this is why. It has less to do with thermodynamics, Matt, and more to do with the human factor.
Correct.
Yeah. Here we've got the room running, in the 60s for the most part. The hot aisle is running up to 80. But at least when someone enters that room, they don't run for the thermostat and try to turn it down.
Exactly.
And this is what I find in cold aisle containment configurations is that someone's always trying to turn the temperature down because they feel it's too hot, when in fact they don't realize that they're standing in the hot aisle when you do either cold aisle containment or cold aisle alignment. So that's two. That one looks like the better one at this point. Let's chase it a little further. Now here what you've done is turn a crack off. This is a test to see, in fact, if it can run N+1. So here you've chosen this one in the upper left-hand corner and switched that off. And this is going to affect a couple different things. For one, it's going to give us a better RTI because we've just dropped approximately 10,000 CFM of air out, and we didn't need it anyway. We had too much. So if we take a look at the summary report now, we can see that the flow through the crack units is 41, and that's come down from 52. So now we're much closer to the 31 than that we need to be. That's going to save energy. So the COP now up to 3. That brings the PUE down to 1.3. We're getting respectable now. Look at the RTI. The RTI came from the 60, 69, 70 up to 76. So that's a reflection of the improvement in the ratios. And RCI high didn't change, which means we're doing a pretty good job with air distribution, because by dropping airflow down, you would think I'd start to get hot spots. We didn't. RCI low stayed about the same. So, and you brought supply temperatures to 60 degrees. They're even across 4 units. So that looks pretty good. And again, if we go and take a look at our recommended temperature inlets, they're all looking pretty good. Beginning to get a little bit of deviation. Again, it's within range, so no problem. Along the tops of these racks, which is not unusual, is where you see it near the top. And that's manageable in terms of where it is. And furthermore, there's opportunity here, I think, to move that supply temp up another few degrees. So this turned out to be pretty good. N+1 is working now. It's now you'd have to go ahead and switch them all off one at a time and go around the room and make sure that the rest of them are okay. But this is a step forward because it didn't conform at all before. So let's go one step further. Now in this case, and I did this one, I took it one step further for purposes of discussion today, Matt, and I said, all right, let's drive the supply air temp up to 70, and let's put VFDs in place, and let's drop them down 30%. So here I wiggled 2 parameters at once. I dropped the total flow rate down for all cracks, down 30%, and assuming we could put VFDs in place. And I assumed the water side economizer, which I believe is applicable in this case, right?
Yes.
And then I drove supply air temp up to 70 degrees aft. Now, this one came out pretty well also. So let's take a look at what we've got. You see now we're down to 36,000 against a requirement of 31,000. So we're getting very close here to being optimal. And if we take a look, now our RTI is at 87%. So we're getting there. Now you do sacrifice a little bit, and I also pushed supply air temp up a little bit here too. And you see that my RCI high began to come down a little bit, which means I'm getting hot in a couple places. But look at my RCI low, 100%. So this means I'm saving a tremendous amount of energy in fan speeds and fan power. Remember, that's a cubic relationship. So as I reduce the fan speed, I save energy at a ratio of greater than a square. Theoretically, it's cubed of the RPM. And also here, because I'm running at a higher supply temp, you see I've moved the supply temps up to 70. The efficiency of the mechanical system goes up. And that ratio is, you know, you're getting about 3.5% for every 1.8 degree F that you move. So, you know, you're getting a couple percent per degree every time you move it. So 10 degrees is worth about 20% of mechanical energy alone, not to mention the economizer window opening up quite broadly. So, you know, we're headed in the right direction here. And if we take a look at our racks, I think we already did that. They're in fairly good shape. You see that we're getting a little bit of red near the top. Now, you and I talked about this a bit. These are the front to tops again, and you're hoping they're going to move those things out, right?
Yes.
Now, if we take a look at the path lines from the hot, and we zoom in tight, you can see again what's going on here. These are beginning to recirculate just a little bit, and you can see it right there. Front to tops beginning to breathe their own exhaust. If we go down here a little further into the section where it's kind of hot, you see they're starting to come around here and breathe their own intake, and that's where you run into it. But it only happens on the tall ones, the very tall ones, and it happens near the top, and it's a manageable situation. For most data center managers, what they do is they understand where the hot spots are going to be, and they just avoid putting high density equipment in those locations. And of course, in a design like this, it's always near the top. Now, you could, you know, do some containment, as we talked about. We did not contain in this place. In this case, we did not put curtains in place or anything, but there could be the opportunity to do that. But this represents, in this one, probably about as good as it can get without getting too carried away. Would you agree?
Yeah.
Yeah. And here, if we take a look at, go ahead.
I was just going to say, when you're reaching for the most cost-effective, there's 100 ways to set it up, and you know the quickest way. All these ideas are very feasible.
Mm-hmm. Here's that 6-foot slice again, and you see that we're running with temperatures in this data center that are, you know, getting upwards of 80 degrees in general in the room. And on the hot side, 90. Now, again, you run the risk here of, and this is at 6 feet. A 3-foot slice would be a little better, a little cooler. So, yeah, there's our 6-foot slice, 3-foot slice right there. So, and if we look at the full range of temperature across the inlets of those racks, you'll see that variation that I'm showing here. Whoops. Of temperature. Let me just do that again, full range. So here's that variation, and you see a little bit of hot getting upwards of 90 degrees near the tops of those racks. So I took the summary reports and put them together so you could take a look as an audience across what we've done and compare them. We started off with a base model with a coefficient of performance of 1.8, PUE of 1.6. We drove it down to around 1.2, assuming economizer was in play. RTI we took from 60%, which is quite poor, all the way to 87.2. In this case, we were dropping all of them down using VFDs. RCI started off 96. Even though we had too much air, we were too hot in certain places. We did get it to 100, but as we began to drive temperature up, we suffered a little bit near the tops of some racks. So this is a judgment call here, whether you turn your supply temp up so that you have no hotspots, or you manage it with respect to where you put your equipment in the racks. We got the RCI low up out of the single, well, below 20 range and moved it to 100. So we're good there. And estimating cost savings to be, 25%, I think that's conservative. I would say it's probably at least 30. 30 is fairly easy. My experience, 30 is pretty easy to get out of these data centers. And you can look at this two ways. I realize here that we are making some assumptions about cost per year because we don't know the averages of these COP numbers. So you can look at it this way and make the assumption that this is an average and that these are fairly representative numbers. Or you can look at it as a percentage, which is kind of nice because a percentage is going to be applicable regardless of what the absolute numbers are. And you see here that we're able to show about 25% from the work we did on this data center alone. All right, so this is a summary slide. Matt, I'll let you just kind of walk through your conclusions on this particular data center.
Okay. So with all the improvements and trying to get the customer the most cost-effective pricing that they can, what we were able to achieve was improved cooling redundancy. By getting the airflow back in the floor, not leaking out through behind the racks, we were able to get into an N+1 capacity, and then they could shut a crack unit down. We have increased cooling capacity. If they wanted to go with an N system, they have more room to expand. We were able to get their PUE reduced, which ultimately returns lower maintenance costs, operating costs, and it's just all around small changes have big impact.
Yep. Great. All right. So, Jen, what I'd like to do here is open it up for questions. We've got about 10, 15 minutes left. I'd like to leave enough time to get a discussion going about what we've presented. Feel free to type into the question and answer chat window. Jen will handle it, and Matt and I will be here on the panel to take any questions.
All right. We do have some questions. So the first one is, what does the process take for gathering and uploading all the data look like? He's looking for key activities and time frames.
And that's to you, Matt, I guess.
Yeah, in this particular data center with 5 crack units, all the information can be gathered in approximately one full day, and that's capturing all the PDU information and the supply and return temperatures and all the CFD or CFM, I'm sorry. So all the technical data can be captured in one day for a room this size.
Mm-hmm. I find it interesting that it's not independent of room size, is it? In other words, the data center can be big, it can be small, it doesn't matter. They're messed up, right?
That's correct.
Mm-hmm. Okay, Jen?
Okay, next one. A presenter at Data Center Dynamics presented his efforts at optimization by installing sensors at numerous points of the data center. I asked him why he didn't use CFD, and he said the CFD is limited because it can't reflect real-time adjustments. He thought this was somewhat true, but obviously our presentation is showing CFD capabilities. What's your view of CFD versus tweaking with installed sensors everywhere?
Well, they're complementary to one another, Jen, and that's you can use them both. Let me be specific. The sensors are existing data. That's what's going on now, and sensors can't tell you what's going to happen in the future. In other words, a sensor can't tell you what's going to happen if the rack load changes by 50%, because it's not a predictive tool. It's a forensic tool. It tells you what's going on now. And yes, you can make changes to the data center dynamically, and the sensor will pick it up, and you'll get a new map. But you don't know what the change is going to do until the sensor picks it up and tells you. And if the change you're making is incorrect, then the sensor is going to quickly tell you that you've made a bad judgment. So they are complementary, and he is right in the sense that CFD is not real-time, but you don't need it to be real-time, nor do you want it to be real-time. In other words, what you have right now is best measured by sensors. Having CFD predict what you have right now is not necessary and not appropriate, other than to validate the simulation model, which is important. Role for simulation is to be used as a way to predict what will happen under a change in condition. It's a predictive tool. Sensors can't do that. They can only measure what is going on right now, not what's going to happen in the future based on a change. So when the instructor said it can't reflect real-time adjustments, he is right. Real-time adjustments are going to be quicker probably than CFD can run it, although it's getting close. You can run CFD in parallel now, and the solve times are coming down. But the converse is also true. The user who made those changes to the data center can't predict what's going to happen either. The sensors certainly can't predict what's going to happen. So it's best to use the CFD model, once calibrated, as a predictive tool of what the future state will look like, what the future situation will be like, so that you know sort of what the possible pitfalls are prior to deployment. Because once you deploy, you've spent the money, and it's very expensive to change it. So it's better to know before you deploy, before you change the racks, before you change the loads. These are simple questions like, where do I put the perf tiles? Or, you know, somebody's coming in here with 15 kW, where do I put it in the room? Or I had a situation the other day where one of my users, who's a colo provider, had a customer want to come in and put 35 kW in 2 racks right beside one another. So we're talking 15 or 17 kW per rack side by side. Where do you put them in the room? Now, sensors aren't going to tell you where to put them in the room. Sensors will certainly tell you when you've put them in the wrong place in the room. But you need a tool that's predictive. And CFD is the only tool you can that exists that is truly predictive. There have been attempts to try to come up with better ways, faster ways. But at this point, there is no better way to do it than the way we're showing you today. Okay?
All right. This attendee might have missed on the actual model that was run for the results, but was the cold aisle isolation deployed for the ends of the aisles, for example, strip or solid doors where a cold aisle ends? The 3-foot or 6-foot heat map that we showed went by fast enough so that he couldn't see whether or not we'd put an end of row baffles in place to prevent cold air leaking out of the end of the cold aisles.
No, I didn't model it that way, Matt, because you didn't have it in yours. I didn't put end caps on the cold aisles of that to model. Certainly easy enough to do and would have been valuable because, of course, cold air falls to the ground and the end caps tend to collect it or keep it in a pool, so to speak. It's like filling a pool with dense cold air. So it certainly would have helped. I don't know what your thought is on containment curtains or what have you, Matt. Maybe you can elaborate on your thoughts on this data center for that kind of thing.
On this particular data center, the reason we didn't put those in was strictly cost-driven.
Yeah.
So the customer wanted the best option. He didn't want to move the racks, but so much. And then, you know, the floor was the biggest issue, and then the curtains was just a cost-effective reason why we didn't put it in.
Yeah, you were kind of on a get-well plan, right? And you had a priority, and curtains came later, I guess, right?
That's correct. I mean, a lot of these data centers you go into existing, you know, based on how they're managed, you have so much airflow leakage, and a lot of the energy efficiencies are lost through the floor. And there's so much to be gained by looking at the floor itself and looking at the air distribution that's where the largest savings are right off the bat. And that's where CFD helps, because if you go in as operations and you look at what the crack units are supposed to do, and then you see what the floor is doing, then you can simulate and you can see exactly where your deficiencies are.
Yep. All right. Anything else, Jen?
I have nothing else. All of the questions have been addressed, and unless anyone has any other feedback for us.
Okay. Well,
I think we do have another quick question. Oh, just looks like a thank you all for us. And I guess on behalf of Paul and Matthew and myself, we thank you for attending another one of our webinars today. We hope to do these at least once a month. And on a separate note, Paul and I will be expoing at the Data Center World Show that's coming up in Las Vegas on April 30th and May 1st. And we look forward to seeing all of you that can attend the show, and we look forward to having you online with us again soon.
yeah, so let me just add to that. If there are others in the audience who have models they'd like to see us present or talk about, or different styles of data centers, different configurations, or you have one that you might be perplexed about and you want us to take a look at, send me a note and we'll consider it for a future broadcast. I want to make sure the material we're presenting is fresh and represents the variety of situations you're facing out there. So if you'd like us to go after one that is a little different or a little unique, I know there's some very different designs out there, please let us know. Drop me a line, send me an email, and we'll consider doing that and vary it any way you'd like. These are really educational. They're for your benefit. And if there's things you'd like to see us pursue, please let us know, and we'll try to get them in a future program. All right?
That sounds good. And we will hand out certificates to those that request them, and the archive will be available in the next few days off of our website. So if you'd like a copy of the presentation, just let us know.
All right. Thank you, Jennifer. Thank you, Matthew, for joining us today. I appreciate it.
Thank you.
You're welcome. Thank you.
Bye now.
Have a good day, all.
Bye.
Bye-bye.
Bye.